Right. So today we're going to continue our discussion on the infinite impulse response filters. We'll actually conclude that in this morning's lecture. If you recall, well, from last week, hopefully you would remember some of the stuff that we did, that in the discrete time world, if you want the best approach to designing transfer functions, whether it's a filter or whatever it is that you're trying to do, is to look and see what was done and what works well in the analog domain. And then you try to convert that to a discrete time version. And in the case of the filter designs, we saw that there were many types of filters that are already used and accepted and very stable and well behaved in the analog domain. So what we try to do is to see if there was some process whereby we can map the behavior of that in the continuous time domain to what we want to happen in the discrete time domain. And we can do that in two ways. We can match either the time response, right? So you have two ways of doing that. You can match time or you can match frequency, right? Last week, Wednesday, we looked at a particular version that mapped time. So we looked at we have a transfer function that behaves a particular way in time, and we try to match that behavior in the discrete time domain. And we call that impulse invariant mapping. And the particular type of mapping that we did was the impulse invariant design. And I ask you all to recall what was the significance of that. Remember, an impulse, when you subject a system to an impulse, what you're basically doing is to subject it to a signal with an incredibly wide, theoretically infinite frequency input. And you then see what is going to happen. And then if you can try to mimic that behavior in your discrete time domain, then hopefully the system will work well. All right, just now, give me half a second here. Okay, thank you, sorry for that. Okay, so what we're going to look at today is what we can do now to match the frequency response. And that particular approach is something called a bilinear transform. Now, the bilinear transform, as I mentioned, for those of you who are starting to get palpitations already, it is not another thing like a Laplace or a Fourier or a Z transform. It's just a two-way mapping, if you like. So you go from one place to the other, and because you can go back and forth, they call it bilinear. All right? Let's see how that works. So if you remember way back when, some lectures ago, when we compared the Z transform to the Laplace transform, we realized that if you make the substitution Z is equal to e to the st, right? That you could, if you do that, that was the actual relationship between the Z transform and the Laplace. And we really went through, remember the kind of approach, if you remember, is that you have the Laplace transform, right? Then from the Laplace transform, you have the Fourier transform. Then from the Fourier transform, you have the discrete Fourier transform, or the DTFT, whichever one. And then between these two, you had the relationship between the continuous time domain and the discrete domain. And then here you had, you remember, S was equal to e to, as we have it here, equal to a j omega, right? And then we could go this way now and let Z, and okay, on this time now we had the Z transform here. And then the relationship between this was a Z with e to the j omega, right? And then between these two now, we realized that we could relate Z and S through this particular little relationship. So everybody has a role to play. It depends on sampling which is very important as we'll see later on. All right. So if you have z equal e to the s capital T, then if I make s the subject of the formula, then s is equal to the natural log of z over T. So what this is saying is that if I have some transform, let's say hs equal 1 over 1 plus s, in theory, I could say that hz should be equal to 1 over 1 plus, and then I have this thing here, natural log z over T. Okay? But then that still gives me a little bit of an issue because the natural log of z is something that I have to evaluate. But I'm getting there. So what we do now is that we take an approximation for that exponential function that we had before, this e to the st. And we use a power series. And if you drag your mind back to some of your CAPE work, something called a Maclaurin series for E. And e to the sts, put in the s here deliberately now, because remember, we have to have the sampling period. So correctly, this should be s here. E to the sts, we express it at the ratio of two e's, e to the sts over 2 and e to the minus sts over 2. And then we expand each of these now, just the first order Maclaurin expansion. So the first order for e to the positive sts over 2 and e to the minus sts over 2. And z is approximately equal to that. Remember, z is equal to this, right? Z is equal to this. We go here, but if we go just to the first term, because remember there's a derivative and another term where that will have an s squared on it, and then a derivative on another term that will have an s cubed, and so you keep going on. We just go into the s, the first order term. All right? And if we have that, then what we have is that z is approximately 2 over ts z minus 1. Sorry, we have z is this, approximately that. And then if I change the subject of the formula now to s, I get s is approximately equal to 2ts z minus 1 over z plus 1. All right? Make sense? Well, up to a point, anyway. Yeah?
Yes, sir.
And we generalize this. You remember what you could do mathematically now. If it's an approximation, then we can put some constant that will take care of whatever other little nuances are in the approximation and make it equal by saying, okay, s is equal to some constant c that, of course, will involve 2 over ts, but something else to make it exactly equal. So that s is equal to some constant c, z minus 1 over z plus 1. So we're now getting into a place where I could, the same if I have 1 over 1 plus s, I now have a place where I could replace this now and put it 1 over 1 plus c z minus 1, z minus 1 over z plus 1, right? And now I have a transfer function. Now this I could work out. So let's see how this is going to work now. We call that particular equation above the bilinear transform. Bilinear basically because the expansion is linear for both the numerator and the denominator. If we were to have expanded to the next order Maclaurin term, we would have had a z squared on the numerator and the denominator. And that would not have been a linear transform at that point in time. Okay, so we restrict it, and any what shall I say, any behavior that is causing it to be approximate, we now take into account by a constant that will now correct everything for us. So let's see how this works. Right? What this is going to do is that the approach now is that we take an analog filter that is going to occupy some continuous frequency range from minus FA to plus FA. And we're going to map this now in somewhere into the digital frequency range. Remember, this keeps coming up all the time, that our analog frequency will run from minus FA to plus FA. Once the discrete frequency range, however, once you have picked Fs, your frequency range is always confined to minus Fs over 2 to plus Fs over 2. Okay? So your range here is from the time you have selected your sampling frequency, your digital frequency range is now confined to plus or minus Fs over 2. Yeah? The analog range, we can pick what we want because we don't have any sampling frequency to deal with in that. Right? And remember now that you have to pick Fs up, appropriately to avoid aliasing. Typically in filter design, we try to pick Fs to be at least 4 times, typically at least 4 times whatever is the filter cutoff frequency that we're trying to design for. Right? So the objective of this approach now is to map FA, which is the analog filter that we know behaves and what we want to use. This is the one, this one is the one that is a function of S into a digital frequency range. And hopefully from this one, we're going to get a function of Z out of that. Yeah. So, and of course, you could put it 2 ways, that S is equal to CZ minus 1 over Z plus 1, or you can express it in front in terms of the negative indices for Z. All right. This is better for DSP. This is easier to work. Okay. So for our purposes, we will use this all the time and then at the end, convert it to the negative indices. Okay, you're less likely to make errors if you're using the positive index version. All right. So remember this. This is one of the things you have to remember. S is CZ minus 1 over Z plus 1. We still have to figure out what C is. All right. And what we want is that, as I said, HZ, which is our digital filter, is supposed to behave in frequency. Remember, this is a frequency transform here. HZ is supposed to behave in frequency close to or identical to what HS behaves in the continuous time domain once we make this substitution, that wherever S is in H of S, we substitute it for C Z minus 1 over Z plus 1. That is the idea behind it. Yeah? Following so far?
Yes, sir.
Right. So the idea is at some analog frequency, the response of HS has to map into some frequency F for the digital filter, where HZ at F is equal to HS at FA. So let's see some manipulations. We're trying to determine what exactly C is. So if we agree with this, right, what I have, remember, I have, this is HS. Right? At some response, typically the cutoff frequency, because that's what they're usually designed for at FA. What I have now, what I want to make is HZ, and whatever HZ does, the response at F here, this response and this response, right, will be the same, right? Remember, this is the magnitude of Hj omega, and this will be the magnitude of Hj big omega. Okay, that is the idea. So let's go back here now. So at FA, which is this one in the analog domain, SA is equal to J omega A, which is J 2 pi FA. That is straightforward. Z is equal e to the STS, which is e to the J 2 pi F TS, or 2 pi F over Fs. Okay, so we substituting now. Remember, S is equal to C Z minus 1 over Z plus 1. S is J 2 pi Fa, and Z is e to the J 2 pi F TS. So we substitute that inside of here. And if you rearrange and you simplify, you get that Fa is C over 2 pi tan pi FTS, right? Or pi F over Fs, however you want to remember it. So we know this because this comes from our analog filter design. We know this. This is what we want, right? So this is the analog. So this is known. F, this is the digital filter cutoff. This is known because we want this. And we know Fs. Known because we choose it. Right? Chosen supposed to have one O. Okay. So we know three of the things here. So we now in a position to calculate C. Right? And if you're trying to figure out how this comes about, this is the same Euler's formula here. Remember Euler's formula, there's one for sine, there's one for cosine. And well, if you know sine and cosine, you can figure out what tan is. All right? All in terms of e to the j. So we know we're in a position to solve for C, sorry. So, and of course, well, you could shorten it if you want. You remember inside of here, however you want to remember it, that omega is 2 pi F over Fs, so that Fa is C over 2 pi tan 0.5 omega. Okay? So this allows us now to map an analog filter frequency, right, which is Fa here, onto the desired digital frequency that we want through this constant C. Everybody following? And this too, need to remember this, right? So two things you need to remember, that S is C Z minus 1 over Z plus 1. This is the bilinear transform, right? This is the bilinear transform or bilinear transformation. And specifically now, C is given by this relationship. And you know everything inside of here, so you could calculate the value of C. We're going to see that in a couple of seconds. All right? Notice now how nonlinear this, and we know this, how nonlinear the relationship is between the analog and the digital frequency range. In other words, in the analog, when Fa is 0, capital omega is 0. When Fa goes to infinity, capital omega goes to pi. In other words, you're crunching the whole infinite analog range. If you like, you could put Fa here, between omega equal minus pi, or as we drew in a little diagram before, minus Fs to plus, minus Fs over 2 to plus Fs over 2. So it's a very nonlinear relationship. And that nonlinear relationship, of course, is because of tan. Tan is a highly nonlinear function. You remember how the tan curve looks, right? It behaves well until you start to approach 0 and 90, and it goes to infinity and so on. All right? This sort of behavior is called warping. For those of you who in the sci-fi domain and like that kind of thing, you would have come across that term before. But warping is really bending. What you're doing is crunching an infinite analog frequency range to fit into Fs plus or minus Fs over 2. This is why, of course, this really determines always what your response is going to be. You have to pick that. All right? Everybody following? Right. So the design steps, like we did before, you get an appropriate analog filter somewhere along the place. Then you match FA and omega. Remember what you have an analog filter whose cutoff frequency is FA. Omega is what I want. So I have a digital filter, let's say the cutoff frequency equal to some FC. What I want from FC, I have to get Fs, of course. From Fs, I get 2 pi F over Fs, which is omega, right? So I know this, I choose this, and I get omega. And then now I am going to match Fa and omega through this function and calculate C. Then I substitute for S using the bilinear transform. So let's see how that works in principle. Everybody with me so far? Yeah? Yeah, no, maybe?
Yes, sir.
All right. Good. So here's a little problem. Design a digital filter using this approach, bilinear response, whose response at 3 kilohertz matches the response of an appropriate analog filter, HS, at 4 radians per second. The design will be based on this particular filter here. And we are assuming a sampling frequency of 12 kilohertz. So graphically, I have HS, so the magnitude of H j omega, whatever this filter, I'm just drawing it like a low pass. I don't know if it really is one. So at 4 radians per second here, and I have magnitude H j omega here, is going to do something, and whatever this does at 3 kilohertz, the response of HS at 4 hertz, this value here, and this value here for HZ, right? So this is the frequency response of HS on this side and HZ on the right, supposed to be equal. That is how it is. So step one, we understand what the problem is. Step two now, we have to match F and omega. So you calculate omega. Omega is 2 pi F over Fs, right? Which is, in this case, 2 pi, and F here is 4 kilohertz. Sorry, 3 kilohertz. So you have 3 kilohertz over 12 kilohertz, right? We already know that omega is that, so we solve. Oops, let me just get rid of my writing here. Boop. Right, so we solve for C. Now, omega A was 4 radians per second. So if you make the substitution here now, FA will be 4 over 2 pi, and then C over 2 pi, and then in this case here, if you substitute the 3 kilohertz and the 12 kilohertz here, you're going to get what else? That's 6 over 3, that is 0.5 pi and is already 0.5 omega, so that will be 0.25 pi. All right? Substitute for there, and you get that C is 4. Right? Tan of 0.25 pi is 1, so C is actually equal to 4. Remember again, keep your calculators in radians when you're doing this kind of thing. So C is 4. So therefore, the transform now is S is equal to 4Z minus 1 into Z plus 1, and you plug that in inside of here. Plug it in, expand. Of course, you will do this. So this is pure algebra from this point. Once you have gotten C, the only mistake you could really make in this approach is to calculate the wrong value of C. Everything else is pure algebra after that. As you can see by holding with the positive powers here, so this is 3 into Z squared plus 2Z plus 1, right, over 31Z squared minus 26Z plus 7, right? And if you expand it out, and then after you've simplified this, you convert it into standard form. Standard form means you go from the positive to the negative in the powers of Z, and you make the first coefficient, right? Remember, this is the B coefficients here and the A coefficients. This will be A0. Standard form means negative Z, 1 and 2, coefficient A0 is equal to 1, right? So you do that, you get it in standard form. I will tell you, and when you do, I've opened up all the past papers that I've put up online and so on, so you could check and see. Sometimes I ask you for standard form, other times I ask you just to simplify it. And if that is the case, you could simplify this and just leave it at that, okay? So it depends on what the question asks for. Pure algebra, once you have gotten the value for for C, make sure you don't make any mistake with that, then the rest is just pure algebra, no set of other maths and so on involved. Okay? And then, of course, the proof, of course, is in the pudding, in the eating, I should say. The proof of the pudding is in the eating. This is what HS looks like, right? HS had a particular response on phase. So let's compare what it is on the left and what it is on the right. All right, sorry, this is my mistake. This is HZ here. Right, so after you have this now, the next step, of course, is to plot if you're able to. So HZ looks like that. Let's compare the two of them. HS is here. HS, HZ. Notice the response at this one at 4 radians per second and at 3 kilohertz. Right? Notice the response is the same. So what you're trying here, if the response is the same at one point, and the idea being that if this behaves at a particular, it has a particular sort of response, and at one point we match what this one is doing at that point, then the mapping is supposed to map try to map the behavioral shape as well. It is an approximation, we know, because we're just doing a first order approximation. But as you can see, it behaves quite well here. One of the things with the bilinear transform, notice that it maps the amplitude response. So you don't need to scale. Remember, that was an issue with the impulse invariant technique that we did last week. This is the impulse response. Remember, it's an infinite impulse response. It actually settles down after about 10 sample periods. It is a second order filter, notice. It's a second order filter, but it takes about 10 sample periods to settle down, to close to 0. Is that good or bad? It depends. As we say, infinite is relative, okay? Infinite has to do with how much memory or how much values it takes before the impulse response actually settles down to something close to zero. This is the canonical representation. Remember what we said, the canonical representation. So the A coefficients are here, the B coefficients are here. Remember, this is the feed forward path, this is the feedback path, okay? And look carefully at the diagram. As I said, you have the choice of putting the signs with the A's here, and then everything is negative, or you can put the positive numbers inside of here, right? So you change the sign around and you put positive and positive here. All right, look at the transfer function. Go back to lecture 14, I believe it was, and see when we draw the transfer functions, right? First off, why you have a choice between putting the negative sign in here or the negative sign on the, either put the coefficients as they exist in here and a negative sign here, or combine the negative sign inside of here and put all sums on the other side. I find this version easier, right? And if you look at the transfer function, straight off here, you would see the values. This one, of course, is not quite the representation. The values are different, right? But to give you an idea, this is what a second order transfer function would look like. Okay. So everybody following? We all right with that? Any questions? Yes. Right? As I say, you have to try this. We have a lot of samples, the problem sets and the past paper. And in another lecture on this that we'll run through doing the sampling class itself. One little thing about the approach though is that the technique that we looked at last week, the impulse invariant techniques, works very well for low pass filters, but it doesn't work if you want to design a high pass filter. And if you remember from our filter discussion, if you know how to design a low pass filter and a high pass filter and a low pass filter, by appropriate combinations of both of them, you can get a notch or a band pass. So really and truly, all you need to know is low pass and high pass. The impulse invariant doesn't give us high pass. It doesn't map a nice high pass filter very well. But the bilinear transform, which is the one that we just did, allows you to take a low pass filter and create a high pass filter directly from it. And you just have to make a very slight modification to the process. So the low pass version, low pass analog to low pass digital, is what we just did. C S Z minus 1 over Z plus 1, and F is equal to C over 2 pi tan 0.5 omega. The low pass analog to high pass digital, notice a little change. It's Z plus 1 over Z minus 1, so the signs get swapped, or the numerator and denominator get swapped. And the mapping coefficient now changes from tan to minus cotan. So instead of here, you replace the tan with minus cotan. So you have FA is minus C over 2 pi cotan 2 cotan 0.5 omega. Remember, the cotan or cotangent is 1 over tan. All right? So you either calculate tan and the reciprocal, but you have to remember this thing, the negative sign. So the numerator and the denominator get swapped, and the tan changes from tan to minus 1 over tan, if you like. Okay? And if you do that, if we repeat the same example for what we did, the last one, if you calculate the mapping values again, just like we did, and you solve for C, you're going to get C is minus 4 in this case. C was plus 4. And then you're going to substitute Z plus 1 over Z minus 1 into the transform. right? And you get that version on this side, and in standard form, this is what you have, all right? So this was unscaled, or sorry, the non-standard versions here, right? And then to get this, now you divide by 7, right? Look at the high frequency response, and notice that the same thing at the response at 3 kilohertz here. The response at 3 kilohertz, well, it's behind a little data point here, so I should remove that, right? And that, of course, matched back to what omega was doing at 4 radians per second, all right? So you have two versions here, all right? And so you can take a stable low-pass analog filter, and you're now able to design either a stable high-pass or a stable low-pass discrete filter. What you need to know, you need to know FA. You must know FA. You must know FS. You must know the digital filter cutoff frequency. And you must decide, is it a low-pass filter I'm designing or a high-pass filter? Once you know that, you calculate the appropriate value of C, and then you make the appropriate substitution in the bilinear transform. So, questions? Everybody following or followed what we did? Yeah, right? Like what we did last time and so on. This is all well and good until you sit down. You have to sit down and do it, okay? With the impulse invariant technique, remember the impulse invariant technique, you start with an HS, then you have to get an HT. So you have an inverse Laplace transform to do here. Then from HT, you get H and T, and then HZ, right? So you have a Z transform to do here and simplify. So in this case, the impulse invariant, you need to remember how to get your inverse transforms to do partial fractions and the like. Then you sample, and then here now, once you get it into the form, you go to your Z transform table and you get HZ and you simplify. In this case here, you start with HS, right? From HS, right, you get this variable C, and then you make a substitution and you get HZ. In both cases, you must know, you must have a sampling frequency, right? You can't do this work without some sort of sampling frequency. The sampling frequency is what gets you from HT to HNT. The sampling frequency down here is what helps you to match FA and FC, right? Once you do that, the rest is just simply not making mistakes, okay? And doing practice and so on. The plotting, of course, the checking of the answers and so on, you either have to do it manually or you use a tool like MATLAB that can calculate the frequency response for you, okay? So, many questions? Questions? Everybody all right? Well, relatively speaking? Yeah?
Yes, sir.
All right, so what we're going to do on Wednesday, we're going to run through some class examples on this. That's the next slide. And then we'll have a look now. So that basically, when Wednesday morning, we'll tidy up with some examples. So we've looked at how to design FIR filters now. We've looked at how to design IIR filters. So now we're entering the last topic, which will be some DSP applications to look at. And we'll start looking at that on Wednesday. All right? Okay, as I said before, if you go on the site, I've unlocked all of the past papers and the problem sets and so on. Probably next Monday morning, or maybe next Monday or next Wednesday, we'll start to have some tutorial sessions to run through some of the problem sets. Some of you have gotten back your midterms already. I'll work with the pile again for those of you who didn't come last week and you're still unable to come on this Wednesday. All right. Okay, so if we have no questions and so on, let me stop the recording. All right, and